world. It's something that I've been investigating for some time now. So before going forward, a bit about me. My name is Nuno. I'm currently an engineering manager at Farfetch. I've worked for all those companies, and you can follow me on Twitter. There's my blog, there's my contacts, so feel free to follow and get in touch. When I was preparing for this talk, I found this sentence that I found very interesting. Like, a good programmer is someone who always looks both ways before crossing a one-way street. So this is really about being safe when we are writing code and making sure that we control all the variables, because software is a messy world, right? Because we always struggle to make things work and work on the happy path, but there's a lot of stuff that we don't control. And this is about good programmers being sure about what they're doing. So before we start, I want you to imagine that you have your car and you're going in your car to drive from point A to point B, because that's what cars are about, right? They provide you the service, your transportation service, to get from wherever you are to wherever you want to go, right? So we usually expect our cars to work, right? So we get on the car, we unlock the car, get on the car, put it to work, and just drive, right? So imagine that you start driving your car and this light goes on, right? The airbag light. So what does this mean? Does this mean that you need to stop immediately? No, it just means that you don't have an airbag. It probably will not stop you from going to point A to point B. Just know that you are not that safe, right? So you can probably go safely for short distances, but if you plan to go on a vacation trip, probably shouldn't go with this alarm on, right? So it doesn't really stop you from using the car. On the other hand, if this light goes on, you might be in trouble, right? Because you have a problem with your engine. So the car might run. You might be able to still drive to some shop to get it fixed. But it's a more serious situation. So when we are building software, it kind of works like this, right? So the way we build software today, it's just a bunch of microservices or libraries that get glued all together, right? And currently we don't have kind of this detailed monitoring of what's happening on the whole ecosystem that provides our service, right? So I want to start by talking about two key concepts. The first one is availability. So this is the definition of availability that goes on the Wikipedia. So availability is the probability that the system will work as required, when required, during the period of a mission. This means that the system has a mission, so it has a time to live, right? And the availability is the system supposed to work when, is the system working when it is supposed to work, right? And if you guys study this problem, you'll get easily into this table. So usually availability is measured by the percentage of time that the system is responding correctly, right? And usually the availability is classified by the number of nines, being the number of nines the percentage of the availability. So a 1-9 system means that the system is available for 90%, which means that it could be down for 36 days in a year, right? And as you go up this scale, you can reach like 4 9s or 5 9s, which would be 52 minutes or 5 minutes a year. And the thing is that each extra 9 that we struggle for, it has an exponential cost. Not only in terms of hardware and stuff, but also in terms of the way the code and the amount of time and effort that we invest to reach that extra 9, right? So this is not an not an easy problem to tackle. On the other hand, the concept of resilience is the ability of a system to gracefully handle and recover from failures. So the question here is this system or this service resilient or not? How will it handle failures of itself or its dependencies? Right? So pretty much the systems that we are building today in our companies and in our business are a bit like this, right? So it's like the iceberg. There's the visible part of the iceberg that everyone sees and uses, like a website, a public API, a mobile application, and then there's all the stuff that's beneath the water level and we don't see it, right? But it's there to support the service. And as the business and the application grows, it's more likely to have way more stuff below the water level than above the water level, right? So this gets pretty complex pretty fast. So picking an example, let's imagine that we have an architecture like this, right? So we have the top layers, not sure if you can see it right, but on the top layers, the blue circles are like end user applications, could be a web application or web API. And below, it's all those systems and databases that are required for that application to work properly, right? And again, the users don't see it necessarily. So imagine that, so you're working on the top layer, right? And let's imagine that there is a failure on some second level dependency, right? And the question is, what's the effect of a failure of a second level or third level dependency on the top level dependency, right? And this is a question that the answer really, it depends on the context, right? It depends on the application. It's up, to your business, right? So there is no universal answer to this question. But we as engineers, we need to ask ourselves this question, right? That's the point. So actually things can go wrong, but in reality, things will go wrong. And that's something that we engineers, when we are planning planning our applications and our systems, we need to take care of this, right? And we need to know that things will go wrong and what are we going to do about it. So in the end of the day, as systems grow in complexity, they also grow in risk linearly, right? So if we have a more complex system, we have more code, more services, more integration between the services, more networking going on, more moving parts, and also more people working on it, right? So there's a lot of variables that will scale along with the scalability of the software, right? So this is something that we need to be concerned about. Some examples of things that can go wrong. For instance, if you are integrating a library within our piece of code, right, there could be an error on the library, and we are not aware of it. We just ran into it, by chance. Or there could be an edge case that we didn't foresee, and then it causes a problem on our application. Hardware fails, right? So not now, we are in the cloud, right? So hardware doesn't fail. But it's me, old school. If you are integrating with external systems or APIs, those APIs could also have programming errors. They could have edge cases that we did not foresee. There could be networking issues. So this is a very pessimistic slide, right? But everything that's here, it's real and it can happen. And I'm not arguing that we should prepare for everything, but we should be aware of things that can happen, or at least the more probable ones, and try to anticipate them and to predict them. And this is a bit of a cliche video. It's very easy for when stuff goes wrong, right? And we get into this mode like, okay, yeah, this is fine, yeah, but it's not. So first thing is that we must assume that the things that we control is the code that we produce, right? So Usually our code has clients. That could be human clients or software clients, and we should not trust them, right? That's first assumption. Second assumption is our code will very likely to use code from other guys, right? Or databases or APIs, and we should not trust either, right? Because we don't have control over them. So, bit of words of advice here. First, when we look at the system or when we start thinking about rolling out a component, we should think about the availability level. So what's the expected availability of this system in terms of business and in terms of engineering? We need to somehow protect ourselves from failures of our dependencies, because if we are working on a system, we are providing a service to someone else, right? And there has to be some kind of SLA going on here. So if I depend on something to provide my service, I need to at least be aware of the level, the service level that I'm getting from my dependencies, right? Make sense? Assume clients will misbehave, right? That's a bit of a given. And this is also the fail fast. So this is a tendency that we are looking in latest years and new applications, that when we fail, we're going to fail fast, right? Because it's better to fail fast than to frustrate the user by waiting for stuff or providing error. So we need to try to fail fast. So before we jump into the code, or not the code, but the techniques, I want to talk a bit about this cycle of when you go and start to work on something, we need to start by planning it, right? So again, what's the availability? What will my component be subject to? And that should somehow influence my design, right? And I'm talking a bit about disaster also, but it's also we also need to be aware of performance, right? So what's the expected load that my system will be subject to? And the answer to those questions should influence the design of the system. And this works both ways, in not to over-engineering and not to under-engineering also, right? So we kind of have to balance it. Then we go to code, then we go to deploy. And at some point, this cycle might need to go back, right? Because we might deploy a service, and the service is a huge success, and then we have to replan it and probably redesign it and probably recode it to the new context, right? So this is really a cycle, more frequent or less frequent, but it should be a cycle. So to get a bit started, two questions. First one, what happens if the service goes down? So your team is responsible for a service. First question is, what will happen if this service becomes unavailable or degrades, right? How fault tolerant are we? How does a failure impact other services? And more important, how does this failure impact business, right? So what's the impact on business, right? Second question, in case of failure, how am I or my team will be able to recover if this fails, right? So are you going to put some self-healing in place, or will it be manual? If it's manual, for manual stuff, I should have at least some kind of documentation written. So there are good practices around here. I won't go deep into that, but it's something just to poke your minds a bit. So what I wanted to focus here is on the part of the code. So the rest of the talk will be about some techniques that we can use to control the reliability of our applications. Okay. So first thing is timeouts, right? It's very common right nowadays for services to use other APIs. So just, make an HTTP call, get the result, and move on, right? So what happens if the application that we are, or the API that we are using, starts responding in like 20 seconds? What will happen to my application, right? So we need to somehow take care of that. The other technique is to use retries, a retry strategy. So I'm going to make a call, and if I get an error, I will retry it. I wouldn't advise using this technique for front-end stuff, because if we are retrying, we are still probably blocking the user from the user experience. But this is very useful for background tasks. Okay, and here we can decide we need to take care of two dimensions. First is timing. Okay, so I got a failure. Will I retry immediately, or will I wait for a bit and then retry again? The second is for perseverance. How many times will the operation be retried? Will it be retried forever until, I don't know, the end of times? Or will the application give up after a number of attempts? These are just questions. I'm sorry, I don't have answers for you today. Another technique is fallback. Right, so if we are calling a system, can I get a fallback value for what I'm trying to get from that other system? If I can, maybe I could use it, right? And this can go hand in hand with cache. So if the results of my invocations to another service or to a database can be cacheable, I can just store it in cache and avoid load, by always making the calls. But I can also use items that are on the cache as a fallback service, as a fallback value. Maybe I can. Okay. When you're talking about cache, we need to think about how will the items in the cache expire, because they should not live forever, right? And here there are two techniques. One is the absolute expiration, which means that I'm going to get some result, make this invocation, and cache it for like 5 minutes. And after 5 minutes, I'll just make the call again and cache it for another 5 minutes. The second is sliding expiration. Sliding expiration means that I'm going to get the value, cache it, and then I will, the expiration will be dynamic, right? And here we have 3 common options. The first is the least frequency used. It means that the items that are not used will go first. The least recently used, that I will remove older items, and the most recently used means that I will remove newer items. So it just depends on the use case. So it's just common options. Typical, but these are usually used, or they should be used in combination, right? And some typical scenarios are in case of a crash or a timeout, retry. In case of a crash or a timeout, just fall back. Or cache it and then fall back if there is no item on the cache. Okay. One topic that who has ever heard of circuit breaker? Okay, a few people in the room. Who uses it? Okay, cool. So what's a circuit breaker? A circuit breaker, it's a pattern that makes my software stops making calls to a system that is unhealthy, right? So if I'm making calls to another system and I notice that I'm getting a lot of errors, or the system just becomes unavailable, it's pointless to try to insist on calling that system, at least for a while, right? So how does this work? This is the machine state that usually is used for circuit breaking frameworks, and this is inspired on the light switches that we have in our home, right? So it's about electricity. So when the circuit is closed, it means that my service will be calling that service. So everything is flowing as normal. So it's closed, right? I'm getting calls between two systems and it's working fine. Whenever I have a number of subsequent failures, could be like 5, 10, 20, whatever you think it's worth, then the circuit breaking framework will detect that and it will open the circuit. It means that it will just stop making calls to the other system. Just stop, right, for a while. And things will be calmer, hopefully. And when you are in this open state, right, we have broken communication. So we have potentially a failing service, right? But how do we know that we can re-enable the communication? That's the F open state. So what happens if we configure the circuit breaking framework to stop making calls for 10 seconds, what happens is that after 10 seconds, it will go to the half open state. And on the half open state, what the framework will do is it will leave one request go by. And if that request is successful, it just gets closed again and gets back to the normal state. If that one request failed, it will remain open. Right? So it kind of sacrifices one request to test the connection. Is it okay now? And then decides whether to open or close. Does it make sense? Yeah, got it? Okay, so this is just the test that what I said. So this is a bit of a typical scenario that we could assemble. So if we have a crash or a timeout, then and if we have that crash or timeout for a given number of consecutive errors, right, I'll break the circuit. And when I break the circuit, I can, if I have a way to provide a default value or something that at least won't break the user experience, I will. Either being from cache or being from a static value that is stored on my application. Make sense? Okay, so going for the demo. Let me just check on the time. Okay, so here I have set up a web application. So this is a web application that is getting this image pixel scan from an avatar service that's running on a web API. So I have two applications running on my laptop, one for the web app, one for the web API. So the way this works is, I can show you here. So if I get an avatar for PixelScamp, it will retrieve an image that is stored on the disk. If the application does not have any image, it will just generate a PNG file with the first words of the sentence, right? Nuno, Caneco, and C, right? So this is the way it works. So this page is simply calling the web API and running some information there and with the date for us just to check what's going on, okay? So in this endpoint I have, oh no, sorry, I was already on the resilient one. So let's start with the naive. So on the naive implementation, what I did is I have an API client on the web application that calls the web API, right? Plain simple. Opens an HTTP connection, makes the get, gets the response, and renders it on the page. Pretty simple, right? So pretty much works as expected. The thing is that I've actually did some things on my web API to introduce some problems here, right? So what I'm going to do is I'm going to call this endpoint that will provoke a delay. So what this will do is if I go to the API. The API will only reply after 5 seconds. So it will wait for 5 seconds and then reply. So what's the effect of that in my experience? So now I have to wait for 5 seconds to get the reply, right? So at this point, one thing that I could do is I could go to the code, and we all know that live coding is dangerous, right, in demos. And I'm just going to add a timeout, right? So now what's going to do is the web application will wait only for 1 second. If I don't get a reply in 1 second, I'll just fail, okay? So, already have some errors on the log, right? But because this is the naive implementation, now I'm getting a timeout exception, and I'm presenting an error to the user, right? So this is far from being ideal, right? Okay, so let's reset the application just to make it work. Okay, so now it's immediately get back. Okay, so on this other endpoint, I have the resilient endpoint. And for this resilient endpoint, I've combined two of those techniques. So I've combined the circuit breaker with the fallback. And on this resilient endpoint, and I will show you the code in a minute. So it's working, right? So I'm refreshing the page, so it's working. And now I'm just going to cause an error. Okay? Which means that now my endpoint is returning a 500. Okay? When I go and get an avatar, I'll get a 500, right? And this is what happens. Because I have, that image of the gray guy, right, on the application, now just, it's not working, so I just go for the fallback. And if we take a look at the logs, you can already see here a message that says preventing connections for 10 seconds. What this means is that the circuit breaker just kicked in, and I got this configured for 3 consecutive errors, and I hit F5 for 3 times. And since I've got 3 consecutive errors, the circuit breaker kicked in and opened the circuit. So it's not doing requests. So every request to the page is not going to the API anymore. Okay. And now if I go back here and do F5, it will, because it got an error, it will be blocked for another 10 seconds. Okay, so it will remain in this state as long as I'm getting errors on the API. So let's get the API back to normal. Okay, so it's now replying, and now it's working. Okay, make sense? Right? So just for you to see a bit, so this is .NET Core. This is .NET Core. I'm using the recommended library for resilience by Microsoft, which is Poly. There are other libraries for other languages. I've used failsafe for Java in the past. So this is the way. I'm going to zoom in a bit, the code. Oh. Just for you to have an idea of how this is assembled. So I have this class API client that is the plain default API client, just opens an HTTP client, performs the get, and gets the byte array. So there's no resilience here. And then on the resilient client, what I do is I use that class, the API client, and I wrap it around these policies. So the first policy is a circuit breaker. And what I'm configuring the circuit breaker to handle the HTTP request exception and the task canceled exception for the timeouts. Okay, and here it's the properties that configure the circuit breaker. So how many exceptions, consecutive exceptions before opening the circuit, the duration of the break. So it's configured for 10 seconds, and it also gives me some callbacks that allow me to put in code to handle transitions in state. So when the circuit is open or the circuit is closed, I can get a callback from my code and do whatever I want. Okay, and then the fallback, right? So the fallback, what's doing just reading the image from the disk and going on with there. So it's pretty simple and pretty unintrusive, right? So it doesn't pollute the original code that makes the HTTP request. Right, so pretty interesting. Okay. So just to give you a perspective of what happens when we go, to some scale, I have prepared a load test that generates moderate tests. Who has here used JMeter in the past? Okay, a couple of people. So JMeter is a tool by Apache, open source tool that's used to make load tests. Okay, so in this test, I have 5 users, just 5 users, making requests continuously, right? So what the user does, it makes a request to the page, gets the answer, and then moves on, right, on an infinite loop. Okay. So let's see what happens when I'm hitting the naive endpoint, right? Okay, so I'm going to start the test. And this is the graph that shows the responses per second, right? So we are around 1,000 requests per second here, okay, on the naive. And the response time is around 4 to 5 milliseconds on average, okay? But, the web API is running, the web application is running, everything is good, right? So now what happens if I go back and introduce the error on the web page? So now I'm getting a lot of logs on the web API. This is fun, right? Fun stuff to analyze. And immediately the response time goes up, right? Because there are a lot of exceptions going on here, and exceptions are expensive. But also, then this is the most important part, the blue line represents the errors, right? So now at this point, I'm throwing errors at my user. Okay, and this is not fun. Okay, and you can also see that the throughput just dropped. It had a huge drop because I was replying at around 100 requests per second, and now it's like 100 or something. Okay, so let me put things back to normal. It will recover, right, and it will go back to where it was. Make sense? Okay. Going to stop it, and let me just capture the screen if you want to compare it later. And I will record this both. Okay, so now let's reset, and instead of hitting the naive endpoint, now let's hit the resilient endpoint and see what happens. Okay. Let's start. Okay, so in terms of requests per second, let's give it a bit of time to stabilize stuff. Now we pay the penalty, right? Because it's now on the 700 requests per second, and we were on 1,000 before, right? So we kind of pay a bit on the penalty of having the circuit breaker running, right? So we are now on the 750 requests per second with a response time from 6 to 7 milliseconds on average per request. But now the fun part comes in, right? So now that I'm inducing errors, there are no more errors on the user, so it's okay-ish. And actually, the request rate just went higher. Why? Because I'm not making HTTP calls anymore, right? The call is just faster because I'm just retrieving a value from from my application. I'm not, making a call to another service. So, on top of not providing a bad experience to the user, I'm also failing faster. Right? Let's go back. And you will see that despite that I've, put the application, the web API on a normal state, it took a while to get back on track where it was. That was because the circuit breaker was still open, right? And it was not making the call, but once he detected that the application was okay, it just goes, okay? Cool, we're cool? Okay, just wanted to show you one more thing, which is, it has become a practice to applications to report on their health state, right? So if you have an application, usually if you're using stuff like Kubernetes, you need to implement this. It's kind of a requirement, but even if you're working with not Kubernetes or some other hosting, it's a good practice, right? So this application actually has an endpoint that reports on the state, on the health of the dependencies, okay? So now it's returning that the web API is good, and if I just kill the web API, I can also do that. It will become false. So now my web application is aware of the state of its dependencies. So if I use a monitoring tool, a proper monitoring tool, which everyone should use, right? If we monitor this endpoint, it will be very easy to track. So in case of disaster, just go to the monitoring tool and check where's the problem, right? So, and by monitoring here, I already know that the problem is on the web API. Right. For a more complex system where we have like hundreds of services running, this is very, very useful for troubleshooting because we go very quickly to the source of the problem, and we are not being, misleaded by information or, going through logs, through lengthy logs, because that's hard. Okay. Cool. Okay, to wrap up, these are two resilience libraries that I've used in the past. Poly for .NET projects, Failsafe for Java projects. They are very similar in concept, so would advise you guys to use it. And this is it for me, so any questions?